Okay, cool. All right. So, uh, well, thank you for inviting me. And I think you would say in Polish, witam panie I panowie. I'm not a Polish speaker, so thanks for inviting me. Tonight, I'll be talking about the tensor and the machine learning ecosystem in Go. And we'll start by surveilling the state of machine learning in Go. See, Python, not Go, is the go-to language for machine learning. And I think that's a pity because I think Go offers much better semantics and much better primitives for machine learning than Python. Okay. Now, I've been a data scientist for many years. And in data science and in machine learning, multi-dimensional arrays are the primary way we do things. See, this stretches all the way back to the Fortran days because it's often cheaper to do things as a bulk process using arrays than using loops. So this is the story of the tensor package, and I want to introduce you to it. So what is the tensor package? This talk involves this package. So the tensor package is basically a performant generic multi-dimensional array for Go. And over the years, as I've developed it, I've learned some tips and tricks on how to extend such a thing, and I'm going to show you some of that. For example, I'm going to show you how to run your code on NVIDIA GPU. So let's begin. Now, we all know what a slice is, don't we? I mean, this is a slice. This is a slice of integers, and this is a slice of my types. So my type, you can see a slice is actually generic, so you can be anything, right? I mean, integer or my type. And what can slices do? What are the basic properties of a slice? Well, the first thing you can do with slices is you can figure out what the length is, right? And the other thing that you can do is figure out how much was actually allocated, the capacity. So we can do this by asking len A and cap B. And when you run this, okay, sorry, this is LSP's failing. Usually, this would be commented out. So if you run this, it will tell you the length is 4 and the capacity is 2. Now, let's go into another dimension. What if we want a matrix of integers? Well, one way to do a matrix of integers is to have a slice of a slice. So let's create one now here. Now, I want to be a bit careful with regards to what a matrix is. So for example, what I have here is not a matrix. It's just a list of lists, okay? A slice of slice is actually not a matrix, but a matrix can be represented, can be made out of a slice out of slice. In order to make this a matrix, you need to actually have uh, three values in this row. So now you have 2 rows and 3 columns, right? And if you run this, you print out nicely this. So this is a matrix of integers, and it has 2 rows, 3 columns, and it's not a bad solution. A slice of a slice is not a bad solution. But when you really need to process things fast, and when you deal with arrays and matrix multiplication, you really do need to make things fast. You need to understand why this is not such a good solution. So let's understand what's going on by looking at something a bit scarier. We're going to look at the pointers. Now, I have written a utility function which helps us visualize these arrays. And what this does is it basically prints the address of each element. So let's have a look at the slice of slice now. So I would call this draw arrays, mat A, and we'll call this slice of slice.png. We'll run this. And then we'll open the file. Now, what you see here, I'll zoom in. what you see here, anything with an ampersand is an address. And when you go from one cell to the next cell, you will see that the difference in the address is 8. And that's to be expected because, well, an integer on my computer is 8. Not necessarily true for all computers. So 9736 plus 8 is 9744. But what I want you to observe is the red ones, right? This 9760 is not connected to 9744. And so what this tells me is that each row is sitting on a different part of memory. They may be close together. For example, 9760 is close to 9744, but this they're not in the same contiguous memory. And this slows down processing time because you'll need to jump around and look for your data when you're doing matrix multiplication, for example. You need to look for your data somewhere else in memory, and that is going to slow things down. So this, I think, is a very good time for me to introduce to you the tensor package. And in the context of programming, a tensor is basically a multi-dimensional array. And we've previously defined an integer matrix with 2 rows and 3 columns. So let's do the same. Right, so let's do the same here. So 2 rows and 3 columns. And I'll explain what with backing is later. So here you see it prints out the array very nicely. When I say array, I mean tensor. Okay, so I will use array and tensor interchangeably. Okay, so right now we can also figure out where in here you ask for a length and capacity with slices. You can do the same for tensors. And it tells you that the shape is 2, 3. And the thing about this library is that you can not only make 2-dimensional matrices, you can make 3-dimensional tensors, like 4-dimensional matrices, and n-dimensional arrays, basically. So let's, for now, visualize the array with the same thing that we did, right? So we can do and let's run the code here. Okay, and let's open tensor.dense.png and zoom in. Now, what I want you to see is that this number 3352 is actually 3344 plus 8. And what this tells me is that the second row, in this case, is part of the same matrix, same slice as the first row. So it's just essentially one giant slice. And I think when I did with backing, you might already have gotten some hint. So with backing means I'm telling Go to use the same single slice, this single slice, as the backing array for this multi-dimensional array. So this entire multi-dimensional array is just one giant slice, and how you read the slice is how it actually becomes a multi-dimensional array. Okay, so in a slice, you can set a value, right? So you can do things like A0 equals to 100 or something like that. Or you can do X equals to get the value of A0. With regards to the tensor package, well, there are 2 ways to do this, and I'll show you both ways. One's the less interesting way and one's the more interesting way. So let's start with the less interesting way. The less interesting way is that the tensor package provides methods. So you can do at. So when it comes to multi-dimensional arrays, you need to define a coordinate. So let's say you want to get row 1, the first row 0, and column 1. So you can do that, right? So at 0, 1, this thing returns an error. We're not going to check errors for now. So what we can do is we can look at what at O1 is, and then also look at the type, which will be an integer, right? You hope it will be an integer and nothing happens. We can also mutate the, we can change the value in the tensor by going t.set at, and then the value, and say 1, 1. 1, 1 would be this one, okay? Row 1 and column 1. And then after that, we can print t itself. Set. Oh, right. Yeah. AT is wrong. So now you see that the tensor was originally this. It's been changed to this. Now this is the boring one. Okay. The next one is a bit more interesting because the tensor library also has a sub library called native, which provides native iterator. And this one's a bit interesting. So, right, let's do this. So my LSP is not working, but if it's working, you'll see it drop down with a bunch of matrix I, matrix F64, and stuff like that. And what net I is basically what net I is. What this is basically a slice of a slice. So let's ask what net I is. So net I is a slice of a slice, right? And net I is basically an int of int. Okay, good. And that means that we can use the traditional net I 0, 1, and we can change this to any random value that we want. But now watch what I'm printing. I'm printing this. So if you run this code, so the original matrix was this. We've modified it to this. But when I change net I 0, 1, we're basically changing the 0th row and the first column. And yeah, what I'm trying to say is that net I is actually linked to the tensor. And to actually see what this means, we can draw some arrays. And I'm going to show you some go to neti.png. And if you open here on the second window, I open the tensor.dense version. So this is the original. On the right side is the original. On the left side is the mutated one. And you'll note that the addresses are exactly the same. So this is yeah, this is one of the very interesting things about NetEye. And yeah, so this is one of the benefits of using the tensor library. You see, you allocate less, and when you allocate less, you don't cause the GC to trigger as much. In the Mat A example, you allocate twice. You allocate one slice here and you allocate one slice here. Whereas with the tensor, you allocate everything up front, and then all you do is just change the way you're reading your big slice. And because of that, you trigger your GC less, your work becomes faster. Now, with slices, you can slice a slice like this, 1 to 2, right? And by analogy, you can also do the same thing. Now, with tensors, you don't have a lot of nice syntax. You cannot do the same thing as you did with NetEye, but the library actually provides you methods to slice your own tensors. So, for example, you can do this, right? T2 t.slice and s0. Now, to slice a slice, what you do is you use the slice method, and this is going to sound a bit confusing. You use the dot slice method, and then you pass in a list of slices. Okay, so what s is basically creates a type called sli, which implements a tensor.slice. Okay, and what a slice is essentially a range. It has a start, an end, and a step. It's defined as an interface. And the reason for this is because when this library was first created, it was created with a very specific goal in mind, which is a whole other talk. And yes, it's not a great name. It's a terrible name, but it's been there for 5 years now. It's too late to change the name. So when you run this, for example, you can see that I've selected the first row. Okay. I can change this and I'll select the second row. But that's not very interesting to see. We are talking about multi-dimensional matrices here, right? So when you have got more dimensions, you have more options. You've got more degrees of freedoms. So you can also slice a slice along a vertical dimension. So right now we are slicing it horizontally like that. But if we want to slice it vertically like that, you know, we can do that. So what you do is you select, put nil here, okay? And what nil basically means is it says select every single row, and then I want to select only the first column. So when you run the code, it selects only the first column. Oh, right, I forgot to save. See, it selects only the first column. And right now, I think it's a very good time to talk about consistencies and inconsistencies. Okay, this library is unashamedly chasing the NumPy API. So let's look at what happens when we use NumPy. Okay, so So here we are creating a matrix that is very similar to the one that I've created. It starts with 0, but you know, it's just a matrix, right? And we can ask the shape of this A. It's 2, 3. So what if we want to do exactly the same slice? So in NumPy, you do it like this. You select every row, and you select column 1. Okay, this returns an array of 1, 4. It's basically 1, 4 vertically. But in NumPy, if you do this, oh, it's slightly different. If you have a delimiter, if you have an ending, suddenly your result changes shape. So let's figure out what the shape is. So when you select just 1 by itself, it returns a vector. It's a slice. But when you choose this, suddenly your shape changes. And you know what, ladies and gentlemen, this is how you introduce bugs into your code. In the tensor package, the semantics of slicing is very consistent. And this is partly because there's no different notion of choosing one and a range of selection. You always slice with a start, a stop, and a step. And in recent months, myself and the Gogonia team have worked even harder on making sure that locking the semantics down so that it's very, very consistent. We've actually written proofs in Coq that the semantics is consistent. So let's talk about reshapes. When I was showing you the Python stuff, we use a reshape. So if you look at the arrays, I told you that this a matrix is essentially one giant slice, and that we're reading this as a 2 rows, 3 columns. But what if we want to read this as a 3 row, 2 column? So 3, 2. If we want to read this as 3 rows and 2 columns, we can, no problems. We just use reshape. Now, the more interesting part is this, right? Draw arrays, T, and we call 2, 3, 3, 2. Okay. So you see that this array used to be like this. It's a 2 rows and 3 columns, and it goes 1, 2, 3, 4, 8, 6, 7, and 3. Now it goes 1, 2, 3, 4, 8, and then 3 becomes in a new row. And to look at it carefully, if you look at 232x.png, and now it's like this. Oh, I think this is the wrong file. This is something from previously. Anyway, this should get the same idea, right? Now it's the same array, but it's viewed differently. I think, let me run this one more time. And okay, I don't know why this is not showing up. But it's basically the same array that's viewed differently, that's all. Ah, I didn't save the file, sorry. Okay, so if you look at 323x, there you go. It's the same array, but it's viewed differently. It's just a matter of shape, and reshaping is a very fundamental operation for tensors. It's much like getting a length and capacity is a fundamental operation for slices. Yeah, so let's go back to here. But what if you want to actually change the angle or rotate the matrix? Well, you need something called transpose. You need to move the data around. So t.t. So transpose means meaning the other side. Pose means position. So we can do this. Let's format this a bit more, okay? T prime. We call it T prime, and we call this T. Now, if you look carefully, T used to be 1, 2, 3 like this, but now when we transpose it, this value is now at the bottom, and this value is now at the top. Okay, so this is different from reshaping, and it's also transposition is also a fundamental operation in tensors. It's also there are no equivalents in slices, but it's fundamental in tensors. So now we know the basic operations of a tensor. All tensors must be able to support reshaping and transpositions and slicing and all that. So what's so special about this library? Why am I telling you so much about this library? Well, this library is pretty generic. You can make tensors of any type. Earlier when I started this talk, you may have noticed about my type. So why don't we create a 3-dimensional tensor of my type? It's a lot to type, so this is what I typed earlier. Oh, I don't have it now, so hang on. So let's create a 3-dimensional tensor of my type. One second. My keyboard's acting a bit fun. Oh, right. Yeah, I'm on different mouse mode player. 2 layers, 3 rows, and 2 columns. Can you imagine that? So what we'll do is we will create my types here. So 2 layers, 2 columns, and 3 rows, right? So this is 1 layer. And now we can create a second layer. We'll just simply copy and paste. Okay, why don't we? Now, if we print this, you will see it printed out like this. This is a three-dimensional tensor. So it's just basically stacked up layers. And you can, with the three-dimensional tensor, you can slice, you can transpose, you can slice, you can do everything you want. And this gives me a lot of power in terms of what I can do with data structures. So for example, I've actually created a spreadsheet using the tensor package as a display option for a DAG as a backend, a directed acyclic graph as a backend. Now, in the majority of times when you do machine learning work, you don't need a tensor that deals with a specific type that you created. The vast majority of machine learning work is done with floating point numbers, and the library actually comes out of the box with a bunch of linear algebra functions. And here, I think I want to give a shout out to the Golang family. See, Gogonia plays very, very nice with Golang. In fact, all the linear algebra stuff, the matrix multiplication, the vector multiplication, they're all shared from Golang. And this is the point that I want to make about this talk, right? Go already has very, very good libraries that allow you to do machine learning. In my experience, working with Go to do machine learning is a lot more pleasurable than using Python. One of the examples that I showed you earlier caused bugs, and I actually ran into that multiple times. And I'm a guy who knows NumPy semantics quite well. So imagine if you've got some people on your team who don't know the semantics as well. So the reason for this is because Go is traditionally known as a statically typed language, and this has benefits because it forces you to think what you're going to do first. Now, I will admit that when I created the tensor package, it adds a bit of dynamic typing. So at runtime, you'll figure out the types of things. But overall, Go is still a very statically typed language. And because I think before I do, I write programs with fewer bugs overall. Furthermore, the Gonam team and the Gogonia team are very, very experienced with Python. And we've learned over our mistakes with Python. The slicing example is one of the things that we've actually improved on from the Python ecosystem. Now, I built Gogonia to do deep learning, and the deep learning part is a whole other talk. But deep learning is mostly done on GPUs nowadays. It's not done on your computer, not done on your CPUs, right? It's done on processors like TPUs and GPUs. So let me close off this talk by showing you exactly how generic the tensor package is. It's so generic that I can run my functions on a GPU. I have created an example in here, and see the heart of modern machine learning is matrix multiplication, which I've explained before. So that's what we're going to do. We're going to run matrix multiplication on the GPU. So this example is pretty short, but it has a lot of extra stuff. All this extra stuff is basically to extend the tensor package to allow it to be used on the GPU. These two lines, for example, is required by CUDA, which requires you to have a thread lock in order to use. If you don't have a thread lock, you cannot access the graphics card. Then here we create an engine. So an engine is what powers all of the tensor library. Almost all operations in the tensor library is powered by an engine. And the library provides some default engines and is smart enough to figure out what you actually need. So for example, if you're only working on float 64s, then there's a specialized engine for float 64s. If you're only working on float 32s, there's a specialized engine for float 32s. And in these specialized engines, there are specialized instructions in assembly that will make things run faster. So it'll run faster using specialized float 32 code assembly and specialized float 64 assembly. And of course, in this case, we need the engine to run on CUDA, the GPU. So we can quickly hop over to look at the definition of the engine, right? So let's look at the engine. So an engine is an interface, but it basically inherits, for a lack of a better word, it inherits from the standard engine. And the rest of this are all metadata. What it really does is it creates a CUDA context so that you can use it. And the rest of these are metadata on what can be allocated and what cannot be allocated, and so that the tensor package understands GPU memory and CUDA understands Go slices. So let's run through the example now. So in here, I'm creating a matrix, a 2-3 matrix called A with the engine E. And I'll say the matrix is a float 64 engine, and I'm going to use S4 So S4 means it's a column wise. So instead of your entire matrix being a row based indexing, you do column based indexing. Okay. And the only reason why you do column based indexing is because graphics cards use column based indexing, whereas CPUs use row based indexing. So there's a lot of flexibility with regards to a tensor package. You can do all these things. So A is a 2-3 matrix, B is a 3-4 matrix, and when you multiply them, you get a 2-4 matrix. Okay. C is a pre-allocated matrix, and with regards to pre-allocation on graphics card, you need to pre-allocate everything. Otherwise, otherwise you won't be able to run anything because yeah, graphics card requires a lot of manual resource management. So these are all resource managements. You need to free the memory on your graphics card, otherwise it will go crazy. Thankfully, we've got defer, so defer is actually very excellent, and I've not had a memory loss, memory leak since. Next, we set the data. So it's basically 1, 2, 3, 4, 5, 6. And then we'll print out the values and we'll look at the values. But before that, we are going to use tensor.matmul. You notice it's tensor.matmul. It's not anything else. It's just exactly what it does, right? It's provided by the package. And then we'll get an accessible version of the data and we'll print it with code. So let's run the example. Oh yeah, these warning functions are basically what happens when you try to access the GPU, and I'm actually doing some upgrades to the GPU library right now. So the older version of the CUDA library had a lot of functions. In the new version, they've actually deprecated most of these, and so when you call it, it actually tells you that it's deprecated. So let's look at the results. A is 1, 2, 3, 4, 5, 6, a matrix, and B is the same, and C is all set to 1000, right? So I've set to 1000. If anything goes wrong, if in this live demo it doesn't do the matrix multiplication, the results will all be 1000, but the results are not. So essentially, what we've done here is we have just done matrix multiplication on the GPU. I'm using an NVIDIA GPU. And so I'm using CUDA. But if you're not an NVIDIA fan, if you are using an ATI graphics card, or if you're using an M1 Apple laptop, well, not to worry. Mark Kramer is actually working on an engine that runs on Vulkan. So it's pretty sick. It runs on all graphics cards. So that's pretty cool. So in conclusion, what I've shown you is that the Tensor library can do a lot, and it's designed so that you don't have to leave your comfortable APIs. Once you understand all these with engine stuff and this standard APIs that is as the same, right? I can have a tensor that's sitting on a network drive, for example, and I did do that. A tensor whose data is mapped to a network drive. You can go very fast once you know all these basic stuff. So what is the ask of this talk? What do I want out of this talk? Why am I telling you all these things? Well, it's simple. I want the tensor library to be the best multi-dimensional array library there is. I want it to be better than Julia, the language. And now in my view, it is already better. As of now, it's already better than NumPy. But in order to really make it the best multi-dimensional array, I do need your help. I need you to use it. And if you find bugs, I want you to report it. And if you can fix it, I would love for you to have a pull request come my way. That was my talk. Thank you.